So as you can see, so the first question here, this we're going to, as promised, we're going to respond to every question as during the summer training school. So some question already got considered. So that's why for the day one, I think we have maybe very few questions left. For the first question, the questioner says, thank you for the wonderful presentation. My question is, how can machine learning be applied to optimization theory? Yeah, so as we mentioned, there are several areas of applications that we can put machine learning to. However, it depends on the specific type of question, problem that we want to address. So machine learning itself actually has its own part of optimization needs. Like ML depends on algorithm. So each algorithm has some set of parameters. So has some set of parameters which need to be optimized. That is, we need to seek for the optimum value of these parameters. Like the example of our k-nearest neighbor, we do discuss. In this kind of, in the k-nearest neighbor, we have k, which is very important, as if you recollect. Yeah, so in this k, you can set the value of k to be 1, it could be 2, it could be 3, depending on the problem you're having. So we want to find out what is the optimal value. This is one way. So in itself, it has its own aspects of it. And there are other optimization algorithms that have often been brought into AI, to machine learning, like the particle swarm optimization, genetic algorithms, and other optimization algorithms that we do call nature-inspired computing methods. That is, they study nature, like they study the way the fish is used to swim in the sea, and they come up with an optimization algorithm. They study the bee, how the bee used to interact. They study the ants and some of the unique activities that are taking place and interaction among them. We have one of the popular is the ant colony optimization and so many others. However, when we talk of optimization as a theory, as another entire field, actually, because the essence is you use something to solve a problem. Even though machine learning has its own optimization needs, however, if you have optimization system that has been carried out in the past, and you have data set for this, then for sure machine learning can actually be applied. So rather than carrying out the optimization, once again, because the idea is you optimize something, maybe you are designing what is the best design that can go with this particular material. There's a material constraint. Instead of having to repeat the optimization every time you need to design this material, you get your previous data. If the data is available, then definitely you can use machine learning to actually predict what's going to be the optimal design that you use. So this is when you look at using machine learning as a means to actually solve optimization related problem. So if the data is available, for sure machine learning can be used to actually, like a lot of design system whereby you need to try several design patterns and then you come up with the best one. So instead of having to try the best, try several patterns all the time, since we have previous data, then we can just make use of machine learning, train it on those data, and then it could actually successfully predict for you acceptable or close to the best possible outcome. Now, that is after extensive training and testing must have been done. So the answer is yes, we can actually apply it to optimization theory and there are different fields, provided there's data. The secret to machine learning, data availability. Now, so question 2, how do you make use of algorithm? So he said, how do you make use of algorithm? I think this came at the early part of the question, of the meeting. So asking, because we later discussed algorithm, we gave an example of an algorithm, which is k-nearest neighbor. That is, it was referring to machine learning algorithm. We later at least show us how we can use machine learning. We have machine learning algorithm like k-nearest neighbor. We described the theoretical basis, and we also demonstrated it using Weka as a very simple platform that anyone can easily make use of. So I want to believe that question must have been solved, and it's already uploaded into our YouTube channel. You see the description of k-nearest neighbor algorithms, well presented. You also have the demonstration of k-nearest algorithm using Weka, where we use it to solve the problem of predicting diabetes disease, the onset of diabetes for someone through questionnaire. It was a very nice data, and we also share the data actually in the available platforms so that people can go and practice that kind of problem, and you cannot extrapolate it to your own area of interest. So in that problem, they try to say, okay, can we really tell if someone is diabetes without necessarily going to clinic? Because one of the motivation from me personally was that even some people are so busy, although they have medical facility, but they are so busy that the few minutes they are going to take off their work to go and look for over their head, they couldn't do that. They kept procrastinating until things get late. You see? And to some, the issue is not that they don't have time. The facilities are just not there. They don't have the medical facility, or they don't have the financial wherewithal. So now the question is, if questionnaire doesn't need any financial stuff, you don't need to pay anything. Once you have access to this kind of set question, you can ask it, and the system can diagnose if you are likely going to have diabetes or not. And also, another motivation for that thing was coming to realize few people I personally knew were diagnosed of late stage diabetes without them knowing actually. You see, people's body are totally different. Some people, they quickly develop some signs of diabetes, like going to toilet regularly, to urinate. But in this case, that person never had any issue, only for him to suddenly complain of eyesight weakness. And they found out that the sugar level was so high that it already started destroying the eye. In this kind of scenario, a very simple machine learning predictive solution could possibly make such people to know ahead of time that, oh, they're already having medical issue. So I remember we used this to to demonstrate the use of k-nearest neighbor. Now, so question 3. Now, please, about the diabetes analysis. Good. Okay, this is what we were talking about. What about if we have more data set with more illness? Are we going to give them 0, 1, 2? Okay. He's talking of when you want to do prediction, we only did prediction we did binary predictive solution. That is the target value, which is Y, is yes or no. Is it diabetic or not diabetes? So because those are the two cases. If you want to predict if somebody is diabetes or not diabetes. Yeah, we can include a third category. Maybe there are some people, they are not diabetes. You cannot say they are fully diabetes, but there may be in between. Sometimes we create it actually. But the more the number of classes you are, the more challenging to get accurate result. It's not impossible, but 3 classes are not more. 3, 4, 5 is still good. The moment your number of classes have become more, 14, 15, then it becomes very challenging to do the classification. We are not saying you cannot do it, but you need more data, or better still, you can partition it into 2 multiple problems. Solve class 1 and 2 first, solve 1 and 3, and then binary by binary, and then you can compare the result later on. However, for this case, let's say somebody wants to have 3 classes instead of 2 classes. That diabetes data was saying, is it diabetes or not? So it's yes or no. But we don't want yes or no. We create another line. We say, okay, diabetes, non-diabetes, and intermediate. Maybe it's about to start. That situation whereby such a system had. In one of our presentations, maybe last few weeks, in this section, we presented COVID-19 anxiety prediction paper. Yeah. And we can see the video on our YouTube channel. In that particular problem, there were 2 types of predictive solution. The first one was predicting anxiety as two-class problem, where you have, is this person having anxiety or not during the COVID-19? Because that was one of the very big issue the medical team need to cope with. People were not really catching COVID, but they got so scared that some of them developed anxiety-related stuff, and some of them went into depression and a host of other problems. So in that case, we mentioned that the first one of targeting is someone having or going to have anxiety or not. It's yes or no. That is binary classification. The second one we did was, the second problem was that in the same paper, trying to solve, is he having anxiety? That is, so is he having anxiety? Is he no anxiety, medium, and also the full-blown one? You see, you have level of that anxiety. So 0, nothing is there, fully or medium. That is, the anxiety level also was measured. In that case, became 3-class problem. So I hope this will answer this question. So if you have more data set with more illnesses, the issue now is, do we have, maybe in few cases, you have diseases that share the same attributes. You see, in that case, you may want to say, okay, like the anxiety I gave now, level of anxiety, it's not different disease, it's the same disease, but they are in different level. 0 means none, it's not having anxiety. 1 means medium, it's having, but not very high. 2 means really serious anxiety. In that case, it is still the same disease, but we are ranking the level of presence of that disease. But the question is saying, if you have more data set with more illnesses, because if you have mostly different illnesses with their different model, you cannot build a model that's going to predict someone is diabetes. At the same time, you want to know is the thyroid cancer. I mean, usually you have different predictive solutions for it. And this is one of the challenging stuff in AI. It's usually to a particular domain, a limited domain. So you need to target each problem one by one. The idea of having a single system that works for multiple illnesses might not really arise. Of course, you can have a kind of a big package wherein you have different diseases inside, but they must have been built separately. So I want to hope that clarify the question. Yeah, thank you very much. So I think we can see Mr. Chris is providing the link to those videos as we actually cite them. Thank you. So we can check out those references, especially the anxiety video, and see we discuss the paper from beginning to the end, especially for academics, for people who are interested in academics, it really be of a strong help, and even others to see how we start machine learning from the beginning to the end, including data description, how to do the analysis of your data, the experimental side, and host of other details. Now, so question, yeah, those are the 3 questions for the day 1 in that particular order. However, before we go to day 2, we got a question this morning, so which we are going to integrate into this. The question says, good day, doctor, I have a quick question. I was part of the attendees of the summer training camp, and alhamdulillah, your classes have really made me interested in ML. I have a question. There are several classifiers out there, so I wanted to ask, what tells you which class of classifier to use, e.g. lazy, function, decision tree, and the others. I've also watched some of your video on selected classifier like SVM and FBEC. Now, so yeah, if one of the concluding part of one of our lecture last week during the summer training was that, you see, there's no machine learning algorithm that is inherently better than others. You see, we have to check out. That is why when you have a data set, no one can tell you, Bidop, that this is the algorithm that is going to work for you. No one. If someone tells you this is the best algorithm, usually it's me that person is maybe he has forgotten or it doesn't have some basic fact about machine learning algorithm. No algorithms work in all situations. So That's why I personally believe in what is often stated, let the data speak. So we have to allow the data to really tell us what's going to happen and what is going to be the best classifier to be used. Not necessarily depending on how someone feels. Now, so in this case, the idea is when you have a data set, we can only give advice. You have data set. If the data set are very few, from my personal experience, I've seen that support vector machine is a good one to go for, and also k-nearest neighbor, very simple one. See, because for algorithms like machine, like artificial neural network, usually it expects you to have sizable data size, a little bit, maybe more of data before it actually, you can also practicalize it. But for SVM, the data is few. Sometimes we get very good, in several cases we get very good results. When others fail, it performs. So, and because of some of the unique capability in the, what we call the ability to propel the data to higher dimensional space, we explained in our previous videos, and hopefully we have another day also talk about some of the unique attributes of support vector machine. For anyone that follow, we will see it in several of our work, because always it worked in several cases for us whenever we solve critical problems, especially when data sets are very few. But still, I'm not saying it's the best always, because that is not a correct statement to say that. So when you have the data set, you also start from the simple. This is the rule of thumb, by the way. Start from the simplest algorithm or one of the simple ones, like k-nearest neighbor. Try to use it. Another one is decision tree. Why? Decision tree, especially if the data is coming from a client who might want to really listen to you to make presentation, how the algorithm is working. Decision trees is usually easier to explain to people who are non-technical compared to people who are technical. So in that respect, k-nearest neighbor, decision tree, and you have justification for it, because in documenting machine learning, one of the expectation is to tell us why you are making the choice of that machine learning algorithm. I'm making k-nearest neighbor because it's very simple to use. I can easily explain to my client, or people can easily understand it. I'm making use of decision tree because client can easily understand, or I'm making use of support vector machine because it has been reported in several work with excellent results, especially in medical, especially in engineering. You have some justification for whatever selection you are making. But however, once you get your data, you don't have prior knowledge about all these algorithms. Of course, you start with the simple one, lazy one, the k-nearest neighbor, then move to decision tree, try neural network, try a couple of Bayesian also, you try a couple of algorithms. And the good news is there's no maximum number of algorithms you can try. For a single problem, you can actually run 15 or more experiments for a single problem and report all of them. Of course, your own time also, you have to consider your time. But minimum number of machine learning algorithm that is expected for any single problem is 2. So that there will be comparison, because machine learning will always want to compare. How is this one performing? Why is this one performing than the other one? There's always room. That comparison is always very important. So run a couple of machine learning algorithms and then try to come up with the one. There will be one or two of them that will be better than the other. Then compare them and then discuss your results. So in summary, there is no specific way you have to, no one would tell you the best machine. In fact, there's no best machine learning algorithm. Rather, we have to start from the simple. And then if none of the simple ones are working, try more complicated ones. If they're not working, then try the ensemble system. Because sometimes some data sets are so tough that no single hypothesis function can understand what is inside it. You remember the principle of hypothesis function we described. You see, sometimes they are so complicated that no single hypothesis function can represent your data set. Maybe the data set is unusual. In that case, we have to combine multiple machine learning algorithms, and often than not, we get better results in this kind of scenarios. And I hope that answered that question. So that is the question for the day one. So we are going to move to the day two question segment. Thank you very much.